just so we don't forget about them.
I think that's a good idea, honestly. I don't multitask all that well when I'm talking. I can't handle the chat and the timer and a bunch of other stuff. So that's fine. I think what we'll do is let's go ahead and have people who are new for the first time unmute and go ahead and say hi and tell us who you are, where you're located, and what you're doing. I think we can go ahead and start that. It is being recorded, and I will, just so you know, be posting this on the YouTube channel and send out that link to everybody after the fact. So again, feel free to go ahead and unmute and introduce yourself to the group if this is your first session. Many of the names I recognize, and some have been via email that I think are new. Happy to have all of you joining today.
I'll start. I'm Cass Seichman, and I am a professor of counseling at Oregon State University, and have a lot of doctoral students, and use JASP, and beginning to use Orange. I just submitted an article, my first article using Orange, and as I've been using Orange and JASP, I realize I need to learn a lot, and so I'm here to learn, and I'm so excited to be here, and thank you.
That's great. I would say it's a sharing experience. I'm sure your insight will contribute to our education as well. This is the beautiful thing about this. I mean, we're continuing to find things in the literature that are misleading, incorrect, and need to be tested. So, and we'll get into that in a minute. Who else would like to unmute and introduce themselves? Don't be shy. But I think we'll go ahead and get started. Again, welcome to everybody, and we're happy that you're on board. A few just general comments, and I'm going to turn it over to Dave, is that this chapter 2 on data basics is long, and it's going to get longer, actually. You may be happy to hear that or sad to hear that. But the point is, there's no question that data is the center of data science. And even in AI, I don't know if you've seen in the literature, leaders like Andrew Ng, who said, I want to see data-centric AI, meaning less focus on the algorithm and more focus on the data, because otherwise it's garbage in, garbage out. And I will say to you, if you go back in the last 15 years and you look at most articles on machine learning and AI, the quality is low. A lot of mistakes were made, incomplete understanding of the literature and what they were supposed to do. So we'll point out some of the pitfalls today. In fact, we're going to focus on largely challenges to data science. These are 4 that we're going to talk about today. There are many more: cursive dimensionality, multicollinearity, data leakage, and data imbalance. These are traps, and that we're going to try to help you through those, and we'll refer to those down the road as well. We've had a couple of other people join us, I'm happy to say. So let me go over a couple of things. Number one, we have added a section, this is due to Dave's genius, on data science experimentation. And what that means, it's going to be a regular standardized pipeline of how do you evaluate a data set with a whole menu of algorithms. What should you include and what should you not forget? And it's going to be something that's going to be in a spreadsheet that we can share that's color coded. I don't want to spend too much time other than saying, to me, this is exciting. I don't think it exists anywhere. David, you want to comment on your data science experimentation section that we will cover?
Yeah, you know, when you're building models, very often the modeler, the person trying to create a predictive model is kind of daunted by all the different options, and they really don't know, you know, okay, what do I do? And then they'll go do a Google search and they'll say, oh, okay, then I guess standardizing my data is I guess better than normalizing. So then they'll do that, but they don't really know for sure. And then they'll maybe read another article that says, no free lunch. And what's good for one data set is not good for another. And then if you Google data science or machine learning experiments, you'll find all kinds of stuff in software how to track your experiments. You will not find any guidelines of how to do an experiment and what experiments you should do. And next month, we're going to do a deeper dive, probably the entire session next month. We'll be talking about all the different, we can't cover every experiment under the sun. We'll give you a lot of different examples, but what we will cover is no matter what experiment you could dream up. And again, why do you do experiments? Is because you're trying to find a better predictive model. And so we're going to show you what is the process of experimentation so that no matter what experiment you dream up, if you follow that process and you compare all the model metrics that we show you and the other types of metrics, that you will then see yourself what is the right decision to make and not having to constantly Google, try to find some guideline that might be right and might not be right.
Okay, thanks. And then the next announcement is that while I'll cover class imbalance superficially, we think it's so important we've now added a new chapter 6 on class imbalance so that we can show you more methods than I think exist in any textbook of how you might handle class imbalance, the pros and the cons and examples. And if I can remember to do it when we finish up here, I'm going to show you how we handled it with using synthetic data and show the workflow that David uses. So kind of kill two birds with one stone. So class imbalance will be a very important chapter. The next one to let you know is I've gotten into, and with David's help, we're experimenting with synthetic data. AI can generate synthetic data largely using a GAN, a generative adversarial network, or AI. Ironically, one of the companies, an earlier AI model called LSTM, long short-term memory, has performed so extremely well. So we'll be talking about synthetic data. We'll be experiment with synthetic data. We will correct data imbalance generating synthetic data. But let me give you the 3 names of the companies we're playing with. There are about 6 right now. These 3 you can access and play with. One of them is Gretel, Gretel. The next one is Y Data, capital Y Data. And the third one is mostly.ai. So if you're interested in synthetic data, I'm giving you those companies, and on your own, you can play with that. Lastly, we are trying to do something that's unusual, and that is we're going to try to create a SMOTE widget for you. When you have class imbalance, we're kind of come up with an orange widget where you can use SMOTE to balance along with all the other techniques. And I might say that we may be able to do it on our own. We recently paid for Orange to create in the test and score widget Matthews correlation coefficient. So very shortly, when you open up Orange and you're running a model, classification model, MCC, or Matthews correlation coefficient, will be now available. So Orange has been very good about doing these things. It costs money to hire software developers, but the point is we'll continue to work with Orange to try to make it better and communicate with them. I think that's all the announcements that I want to go over. So Dave, I'd like to turn it over to you.
Okay, thanks, Bob. So we're going to cover, as Bob said, 4 sections. I'm going to cover the first 2, and then at roughly the halfway point, and Bob, just give me a reminder when we hit kind of the halfway point where I start to either slow down or I've already handed over to you. I'm going to talk about the curse of dimensionality, which we're going to cover just very shortly at only 1 paragraph here. And then when you look at multicollinearity, which is a very large, important topic in machine learning, AI, and statistics especially, that'll cover the bulk of what I'm going to talk about. So what is the curse of dimensionality? And there's a variety of different curses and and myths that need to be busted in the world of AI and ML. And we're going to try to, in the course of this book, go through all of them. But the curse of dimensionality in general is when you have way too many predictor variables or categories that you're trying to analyze at the same time. And why is it a curse? Well, depending on what type of computational hardware you're dealing with, it could slow down the analysis dramatically. So how do you know when you actually have so-called high dimensionality data? Well, typically what you could read is if you have more than 100 features. And what is a feature? A feature is a column. What is a column? A column is usually a predictor variable in your data. If you have more than 100 of these predictors, it's considered high dimensionality. And that'll kind of mess up a lot of the models. It'll make things more complicated. And to be quite very honest, if you have 100 predictor variables, when you're starting out in data mining, you might have thousands actually. It's not uncommon in the world of data mining and AI where you could have over 1,000 different variables. One of the first things you want to do in your data set is reduce the model, and it's called feature reduction. And what does feature reduction mean? It means that you're taking out some of those columns, and there are a variety of different ways to take them out. You can't just say, oh, I don't like that column, I'm going to throw it out. Or it's not a subjective method, it's a very, very objective method that we use. And a concept called principal component analysis, PCA, you can see it's listed at the bottom, which we're going to cover in much more detail later. That's one of the methods. Actually, a method called lasso regression. It could be used for classification, multiple regression, or for multiple, continuous variable regression. That also has some methods for creating what is referred to as sparse models. Now, what the heck is a sparse model? So a sparse model means that, well, I had originally 100 predictors and I knocked it down to maybe 15 that are very significant. So the model that has only 15 would be referred to as a sparse model. So in other words, you use some analysis techniques to narrow down which of the factors are the most important. And then what PCA actually does, principal components analysis, it actually combines different columns into a new super column or a super feature, or what's called in components analysis is called a super component. And again, we'll cover that later. So those are ways to kind of simplify the model. And especially when you're doing predictor variable ranks, is very important to, narrow down the field so that you're not looking at a long list of, 100 or hundreds of factors. So multicollinearity. Multicollinearity, very interesting topic, and it also aids in the analysis of creating sparse models or reducing the features and helping you to deal with the curse of dimensionality. And first of all, what in the world is multicollinearity? It's a long word, and I wish they were in the world of statistics. We don't make up these terms; somebody else did. And so, what is multicollinearity? It's when you have a bunch of the predictor variables that are actually highly correlated with each other. And especially when you're doing data mining, it could very easily happen. And you say, okay, what does that mean exactly? Well, let's see if I have one column that says, all right, I got a bunch of daily data on the weather. And one column says, what are the number of days for a year or a month where it's sunny? And I get another column right next to it that says, what are the number of days where it is cloudy? Well, guess what? You have duplicate information, because in the one column where it says days that it's sunny, well, if you put in there a 0 and 1 for that column, 1 means yes, 0 means no, I already have the information. If it's not sunny, I don't need a separate column for that. So that's just one very simple example of, you would have two columns next to each other, and there are methods we're going to show you where you could identify mathematically how they're correlated with each other. And when they're highly correlated with each other, you have a choice to make and say, okay, now which one of those are you going to throw out? Because it's redundant, superficial information. So you need to take that out. So, and we'll talk about how that works. Now here's another interesting point. In statistics, multicollinearity is really a killer. It will absolutely paralyze your multiple regression models. It'll make them so invalid, it'll spin your head. So it is an incredibly important topic for the world of statistics. It is less dramatic in its effect to the world of machine learning, predictive modeling, and AI models. However, some algorithms are a little bit less sensitive to them and some are not. But again, you can't just say, all right, I'm going to use an algorithm that's, not sensitive to it, because then it might take away, a model that's very high performing for you. But even in the world of machine learning AI, where that, like I said, multicollinearity might not be a huge impact on the accuracy of your model, one thing for sure it's going to mess with is when you try to ask the model, all right, what is my predictor variable rank? It will totally mess with that. So you have to deal with that. If you want to have explainable model and not a black box where that, hey, trust me, if you just say, hey, trust me, don't ask any questions, then you don't need to have to worry about the VIFs, which we call them. I'll get into that. It's another synonym of high collinearity. But if you ever want to be able to explain this model to other people, you have to deal with it, even if you're in a machine learning model. So another synonym for this whole high multicollinearity is called a VIF, V-I-F. It's called a variance inflation factor. Unfortunately, we have an exact number for that, and we know how to calculate that, and we'll show you how to do that. And JASP, with the help of JASP, and again, as we mentioned last time, we're going to bounce between JASP and Orange, and they're both no code and they're both fairly easy to use. If you have anything higher than a 5, a VIF higher than 5, it is giving you a strong hint. Hey, you got some multicollinearity here. You got some co-correlated variables you're going to have to deal with. And there's other methods that also deal with that. So what does that look like? Multicollinearity in a model. So I tried to, show a graphic here. Let's look at the model, the little graphic on the left here. You got 6 different predictor variables, which are predictive variables we're always going to call an X. The Y is going to always be your target variable that you're trying to predict. And what you can see here in this, graphic is we don't have any overlaps in these X bubbles. So what it means in this illustration here, this schematic, is that, well, that means that they're not correlated with each other. They're just correlated with the predictor variable, which is a good thing. So you're good to go. You don't need to have to worry about, okay, how do I deal with this? But on the right, you could see a situation which is usually more common. And the more variables you have, the more dimensions you have to deal with, you will have, it's a very common situation that you're going to see is something off to the right. You might have 2, 3, 4, you might have 5 different predictor variables that are actually correlated with each other. And you got to sort all that out. Again, you got to sort all that out in machine learning if you ever want to be able to explain this model to other people. And we're going to show you, some situations for how to deal with that. And there's one key point, as you remember here, that Bob explained in one of the weeks, that we're going to always have, key points here when we get through different parts of the book here. And the main thing to remember here is that multicollinearity is not your friend, even in machine learning. So if you Google it and you say, oh, don't worry about it, the algorithms are impervious to machine learning. Yeah, they might be from the predictive modeling part of it. But like I said, it'll throw out and it'll greatly jeopardize your ability to use that to explain the model to anybody. So it's not your friend. So learn how to deal with it, even if it's in machine learning. So how do we start to find these different types of correlations that exist between predictors? There's a variety of different ways we could do that. And one of the ways here we have, this workflow in orange allows us to take each predictor variable we have, which we're going to have in columns, and test a correlation against each one of them. And the two typical types of correlations you do for what we call pairwise correlation is where you're doing, you're looking at just two at a time, which is why we call it pairwise. We have the Spearman, and then we also have the Pearson correlation, and there's differences. And then we have, and you can see in this workflow widget, you could attach the scatter plot to it, and then it'll show you what they actually look like. And I'll show you some examples, and I'll also explain very shortly what the differences between the Pearson and the Spearman. So first of all, when we get numbers from the Pearson and the Spearman correlation coefficients, what do they mean? Well, if we get a high number, what is a high number? What's going to range from, these coefficients, they could range from -1 all the way to +1. And when you get into the plus territory, the closer you get to 1 means you have a positive correlation. If you're at the 0, then there's nothing correlating whatsoever. And if you have a -1, that means that there's a negative correlation. And what do negative correlations look like? I'll show you what that looks like. So obviously, the higher the number, either positively or negative, tells you you have a high correlation between, again, the predictor variables. And again, in this whole section, we're not talking about the correlation between a predictor variable and a target variable. We're talking about the correlation between variables that can mess up either the model itself or the explainability of the model. So what is a Pearson correlation coefficient, which is very commonly used in as well as the Spearman? Well, it basically tests if you have a linear relationship between two variables, and I'll show you some examples. So if you do a typical scatter plot, x1 one variable and x2 the other variable on the xy scatter plot, and the more they seem to look like a line, then you're going to have a higher Pearson correlation. Now, the Spearman is a little bit different. Yeah, if it's in a straight line, yeah, it'll give you a high Spearman value, but it'll also give you a high Spearman value if it goes flat for a while and it starts to move up toward a direction, which means it's not linear. But as long as the XY relationship looked at from left to right, and if you connect the dots, so to say, in your mind, and as long as it is continually increasing or continually decreasing, the Spearman coefficient will also increase. So it's two different ways of looking at it. And again, positively or negatively. And then we also have available in orange, we have what's called the false discovery rate. And it's also tells you is another value we get that tells you how good things are looking and how many things are maybe off the reservation and maybe not good for consideration. So it also gives you that value. And then this key point here mentions what I already mentioned before. Now, when you go into the correlation widget in orange, you get something like the top left. So it's going to list from the highest to the lowest. It's going to say, hey, my highest set of pairs is hip versus weight. And this is a data set that's looking at what correlates to high levels of percentage body fat. And it says, and that's got a correlation coefficient of 0.91, which is pretty high. Then you get another one, abdomen versus chest. So it's going to go down each pair. You could scroll down, it's going to look at each possible pair and show you what it looks like. And then you could also output that table in orange into a data table, and it looks like this. And it will automatically also give you the FDR, the false discovery rate. And you could then start to analyze and contemplate and meditate over that type of information. Now, again, this is pairwise predictions. Now, you saw in the workflow where I attached, after the correlation widget in orange, I attached a scatter plot widget. So whichever pair of factors you have highlighted in the correlation widget, it'll automatically create this scatter plot from which you can then color code if you want to, and it'll then show you, here's the line that the Pearson is looking at, and it'll show you how good or how bad the correlation between these different values like hip, X value, weight, the Y value, what they look like. So it shows you some examples here. Now, that's all wonderful, looking at one at a time, but if we get a long list and we have, of factors and we want to see what they look like on one graphic, we would go into JASP and do what's called a correlation plot. And we're going to always, in there, every time we talk about JASP, we're going to show you, here's the command string for getting, a JASP correlation plot. And this will automatically, if you put in all the different X's you want to compare with each other, it'll automatically create a scatter plot for every possible combination in the data that you had. And you can just then visually scan this and say, okay, they're all pretty linearly correlated. And oh, by the way, they all look pretty highly correlated. So that's an issue I got to deal with. And we can also create what's called a heat map for those correlation coefficients, which kind of distills it and makes it a little bit easier to look at. And I'll show you how to do that. And how you do that again in JASP is you go into regression correlation, you follow this command string, and you finally say, I want a heat map. And what this does, it gives you the same information that we have in the pairwise analysis in orange, and also all those individual scatter plots, but here try to condenses it to one color-coded correlation matrix. This one happens to be the Pearson correlation. And the darker the numbers, the higher the correlation coefficient. You can see a really dark number here is 0.914, really light number is 0.254, and so on. So this again is just another way to tell you how much multicollinearity do I got in my data set. And here we could say, oh my goodness, I got quite a bit I got to deal with. And then if you go into the paint widget, which we don't have the time to show you how to do, but if you go into the paint widget using this workflow, you could actually create theoretical relationships and pass it on to the correlation widget in orange. Like I drew these by hand with the paint widget, pass it off to the correlation matrix, and it'll tell you, all right, Pearson 0.82, Spearman 0.1. And here you can see the difference. It's not a straight line, so it's not a 1.0 in Pearson, but it is progressively moving in the same direction, which said Spearman says, I like it, I'm giving it a 1. And Pearson said, I don't quite like it, I'm giving it a 0.8. And you can see a bunch of different examples here, and you can see where the Pearson and the Spearman 100% agree with each other is the far right one, where it's almost creating a straight line. And in that situation, the Pearson and the Spearman correlation coefficients are going to both say 1. And oh, by the way, if they go down descending, it's going to all be the same thing, just with a negative number. And here we see a situation where that we have pretty lousy Spearman and Pearson correlations. That's when things go sideways. They're not trending up or they're not trending down, or they're doing some other goofy thing. And there's a bunch of different examples here where that you get on the top some pretty terrible Pearson and Spearman correlation coefficients, and on the bottom you have some pretty good ones, but they're negative, for one example at least. And there's just more examples here of comparisons between Pearson and Spearman that you get to look at, right, to see what they look like. Now, you might say, all right, no, is that how I'm really supposed to look at this multicollinearity? Well, let's call that, everything I just showed you up until now, let's call it multicollinearity 101. Now, when you get into like the gold standard of how you really know what is a high multicollinearity, we want to actually measure the VIF. And like I said before, a VIF of 5 or greater, and I give a bunch of examples of what the numbers mean, is something we need to be concerned about. Now, why should we be concerned about that? Well, let me just give you an example. Hey, what does a VIF actually mean, a 5? A VIF of 5 means that there's the R squared of all the other predictor variables is actually 80%. When you're looking at a specific predictor variable, it's got 80% of baggage that is totally correlating just with it itself. And when the VIF gets higher than 5, so does the R squared. And here's the equation for the VIF. Don't have enough time to actually go through that in detail, but it's all here. But what I've created here is a conversion chart that, let me tone it down a little bit so you can see it. It shows you exactly what it looks like if you say, all right, what is my VIF? You see the vertical axis is the VIF number. And again, you know, kind of a logarithmic scale. And the y-axis is the R squared that you would have for that factor and all the other factors that correlate to it. And you can see here for anything above a 5, let's say, for example, if I had a VIF of 125, if I had a VIF of 125, I would have an R squared value of 99.2%. And obviously that means that there's a lot of baggage in your regression model that is correlating with each other, and you need to take care of that. And I already mentioned one example of rainy days versus cloudy days. There's a bunch of other examples that are covered here in this chapter that you could look at, and we don't have the time to get into. But if you want to look at a very quick way of finding out what your VIFs are, you could go under JASP and follow this command, and you get this multiple regression table here of all the predictor variables. And off on the far right, if you check the collinearity diagnostics, you will see that you get a column for VIFs. And I've highlighted everything that's above 5. And you can see here, one of them was actually a value of 33. Now that's pretty high. That, that's telling you that you got, extreme multicollinearity that you got to figure out how to deal with. And like I said, multicollinearity is going to really play a number and mess up your variable ranks. And you can see here, if I go into orange and I do a variable rank, and if you look at what the VIFs are for that variable rank, you can see that they're all the top 5 ranks that I might say, oh, wow, I get a great rank. I'm going to explain this to all my stakeholders. Well, if you look at the high VIF values, that pretty much invalidates the explainability story you want to tell them. And there are ways in orange how to deal with that. There's something called lasso regression. We don't have a whole lot of time to talk about that. Lasso regression will automatically tone down and weed out the high VIFs. And you can see on the right, when I did lasso multiple regression versus classic and doing nothing on the left, you could, where I had high VIFs, I got very low VIFs on the right. And what it does, it uses a trick. It plays with the numerical coefficients in the regression equation. And the ones that are highly correlated, it gives them a very low number, and it drops them automatically low on the rank list and gets them out of the predictive model, and not only makes a cleaner predictive model, but makes the explainability very clean to a lot of other stakeholders. So you go back in this lasso model and you do multiple regression in JASP, you can see now that the VIFs, you say, what do my VIFs look like? You can see they're toned down because I'm only looking at the top 5 factors. Everything's well below 5. So we don't have any major issues to deal with. So again, as I complete this section, we'll talk about, there's a lot of chat questions. We'll maybe talk about those either now or later. Bob, we could figure out when to do that. Multiple regression is really the main and best way to identify multicollinearity, and then also use that as a platform from which to address multicollinearity. So Bob, I don't know if you had a chance to look at some of the chats. Is there anything that I haven't covered?
No, I think we could certainly entertain any questions, particularly about multicollinearity right now. I would suggest that people read this carefully and feel free to email Dave or I with questions. I know this is a lot to consume, so to speak, a lot to unpack. But again, there is a movement about to try to get people, I think there is a book, in fact, I think it's called something about going against model land. But whole point was, don't focus your whole attention on the algorithm. Get back to the basics of how good is the data, and did you pre-process it correctly, and did you look for data traps? So I just think, again, this is going to be a theme in this book and these workshops about trying to teach you things that you don't read in articles very often. I know I haven't seen much about any of this content in the data science books that I've read. So I think this is unique information, but helpful information. And I do think that clearly data is the cornerstone of data science. It goes without saying. All right. So I'm going to cover be a little bit, let me get this back down, topics that are also important. I'm getting there. There we go. Let me increase the size here. You all seeing that okay? Is that fairly clear?
I don't see it yet, Bob.
Oh, okay. What I think is I need to
I
find.
unshared. You got to share your
Yeah,
screen.
I need to share my screen. Yeah.
Yeah, right.
Okay.
There we go.
There it is.
Yeah.
All right. Moving the menus around so I can see my own screen. Okay, so I'm going to cover data leakage and data imbalance. Now, you can actually read articles that say data leakage is a privacy issue. We're not talking about that at all. What we're talking about is a model where it's training on information it has no business seeing. In other words, it biases the model because there's something in the model that it has no business being there, and it gives it clues and hints that will end up causing it to have overly optimistic results. And so there's different permutations of what data leakage is that we'll go over. But in essence, it creates a model that doesn't work well on test data of any kind, be it internal or external test data. And I point you to a very recent article that focused on this. And when they went back and looked at a lot of the published articles that compared, let's just say, XGBoost with logistic regression, when they went in and basically determined there was data leakage because the study was designed poorly, there was no advantage over logistic regression. This is not the first study to suggest something like that, by the way. So this is another study that's highly critical on the methodology of many studies. So this is important to you. I've cited that article, or I can give you that reference, that it is just very important. And understand, I highlighted, if code is not shared, there could be data leakage that is undetected. I'm sure you realize that most people don't share data in their article, partly because of HIPAA, but also that they don't share the code. Theoretically, what you're supposed to do in an article is put your Python or R code in GitHub and then link to it. But that often is not done. So how can a reader go in and question, for instance, when did they split the data? Did they pre-process before or after the split, and so forth? So on top of that, when you look at most national and international guidelines on data science and modeling, predictive analytics, you don't see much about data leakage, which is totally surprising. And so these authors did come up with some other comments about this. And one of the take-home points here that should be boldened, and I actually should be a key point here. If it's not, let's see, I thought it was, but maybe not, it should be, is that test set must be separated before pre-processing, modeling, and evaluation. So without early separation, there could be data leakage. So the very first thing you're going to do with a large data set is split it into test and train. However, I want to say something that sounds like a contradiction. If your whole goal in Orange today with the new data set is just get a ballpark figure, in other words, is this model even worth thinking about? You think the data is good and so forth, then I don't think anybody could fault you of just go ahead and connecting several algorithms, go in there to test and score, do cross-validation, say 10-fold cross-validation and get a ballpark figure, okay? Or if it's a very tiny data set and you just can't split it because your test data would be so tiny it would not be worthwhile, we understand that. But let's say you have 5,000 patients, so you have enough data. The answer is you really should do a test split initially, leave the test set totally alone. If you're going to process and impute and do other stuff with the training data, fine, but leave the test set alone. Also, and that's what the second B is about feature selection on training and test. Featured ranking should be done after the data is split, not before. So it's only done on the training. And the third thing is duplicate should be removed before the split. So you do need to look for that. Remember, Orange has a duplicate widget to look for that. The second thing that is a little bit more complicated, but it's a little bit of a no-brainer in reality is you don't want to proxy in your predictors, your features that you're not thinking about. For instance, I use this example. You're trying to predict hypertension, who's going to develop hypertension, and one of the columns is their medication. If the medication is antihypertensive, obviously you're going to predict that fairly well. So you want to be sure, again, that the model is not seeing information it has no business seeing when it's training. So there are other aspects here that they point out, they call temporal leakage. It should not have data that can, or a test set should not contain data from a date before the training set. Obviously, the training and test should be on different people, not on the same patient. Sampling bias and test distribution. Spatial bias is when you're choosing test data from a geographical area but make claims about it in some other area. And selection bias is choosing a non-representative subset for evaluation that does not reflect the population of interest. Let me comment that one of the articles highly critical on early AI studies showed that they were testing on a group of patients, let's say, by radiologists, and then testing on a totally different group of patients from somewhere else that the radiology resident had labeled or interpreted. They were not apples and apples, in other words. I think now people are more cautious. I think the studies are of higher quality, but I'm just trying to sensitize you to the fact that the quality of the early studies was poor and way overly optimistic, not to mention the cherry picking. Okay, I'm going to move on to class imbalance. If you have questions, please put them in the chat. Class imbalance is a common problem with classification. In the medical data and medical realm, so often the class that you're interested in, let's say cancer, maybe only 5% or 10% of the biopsies, the rest are benign. And what happens is you get pretty decent AUCs and accuracy, but everything else is misleading. And I will show you an actual Orange workflow where we take the stroke patients of 5% strokes, we analyze it without doing anything, not trying to balance it. And we balance it by basically generating 4,600 stroke patients. That is, we take those people who had a stroke, 249 out of the 5,000 roughly. We basically generate more of those types of people based on statistical similarities. So we now have 4,600 that we can add to the 249 and balance it. And I want to show you the difference in the model performance before and after. Now, just like dimensionality reduction, is difficult to define when is too many features. The same could be true of imbalance. You know, Google rates it one way, Kaggle rates it another. I would probably disagree with this when they talk about 100-to-1 is moderately imbalanced. The stroke data set is 20-to-1, and it's severely affected its performance. So again, there is no national standard to tell you exactly what it is. There is one Pearl, and hopefully you remember to check it every chance you get is in the data sampler when you're splitting into test and train. There's a box that says stratified. Be sure that's always checked. What that is, again, refresh your memory, is let's say you again have 5% cancer patients. Well, when you go to do k-fold cross-validation, the stratifier will be sure that 5% appears in every fold. Otherwise, you might have a fold with 0 cancer patients, for instance. So this just keeps it the playing field level by being sure that the percentage or proportion of minority patients are the same in each data set and fold. So I do want to emphasize that there is no one size fits all to the solution. And in the chapter on class imbalance, we'll be going into that in great detail. But this is another reason to promote the idea, you know, of data scientists, and particularly David, that you need to set up experiments. And in Orange, frankly, it makes it much easier to set up your dual workflow, one imbalanced, which is what you're dealing with initially, and one balanced once you've made some, you know, changes using techniques like SMOT, random oversampling, and synthetic data, and see how it affects performance. So again, I do refer people to chapter 6 coming up. That we'll go into more detail than Jason Brownlee or any other book that I'm aware of. We'll go over more ways to crack the nut. So this one I mentioned, these are ways that you can use to evaluate a model's performance with imbalanced data. Right now it says that it's not available in Orange, but it will be shortly. We know that Matthew's correlation coefficient is a great metrics because it measures the performance of your model for the minority class and the majority class and averages. So overall, how good is your model? A lot of people recommend always having this for a classification model. That's why we wanted to see Orange added. It's a nice feature, and we'll cover that in more detail. We'll cover precision recall curve in more detail, but that's what's recommended rather than the receiver operator curve if you have class imbalance. And so the measurement of that, the area under the PRC is the AU-PRC, and we don't need to worry about that now. Now, here's one that's a little bit more controversial that Dave and I'll have to settle, because I think he's seen literature to suggest log loss is useful with class imbalance, and I've seen literature suggest it's not useful. So we're going to run some experiments ourselves and try to come up with our own conclusion. So just understand more to follow on that one. And then the F1 is called the harmonic mean of position and recall. It's just a good overall metrics. If you have a class imbalance, often the F1 score is low, and that's one of your tip-offs. In fact, I'm going to show you, let me try to bring up the workflow here. I don't know. I don't see my bottom menu is the problem. Let me see if I can get rid of this file. Okay, now. All right, I realize this is sort of, it looks like a spider. But with Orange, it's not that complicated. I don't know, I'm not moving it. Dave, any ideas why the cursor wouldn't move? I wonder. Let me try to enlarge.
So you click down there and it's not doing anything on the workflow?
Now it is. I had
Okay.
to maximize it. But
Okay.
basically on the left here, And again, some of this is blocked. I don't know if you can see it, but in the top, it says original real imbalanced data. And to make a long story short, we have connected it to obviously these classifiers so we can see how it did classifying stroke and no stroke. There's 5,000 patients. You can open this up and see if that'll show up. Yeah, so there's 5,100 instances or rows. There's 10 features. And there's two, stroke and no stroke is the outcome. So what Dave has done is he's created the classification, but he's created other things that I won't get into right now, but we will get into. Other ways that looking at this model is similar, looking at the performance of the model, number one, but number two, how does it compare with the data set you balanced? So the 5,110 has only 5% stroke. Let's look at the performance of that. And you'll notice, once again, my menu's in the way. Notice that the AUC for, say, random forest, not too bad. Logistic regression is good. Accuracy is dynamite. It's wonderful. Specificity is too good to believe. 1, meaning, it can pick up all negatives as true negatives, but then all of a sudden now look at precision, 0, 0.1, there's a 1, which makes no sense. And then recall, which is sensitivity, look how low it is. So the point, I think you should conclude by that, I don't know how to interpret that. My model is so imbalanced, I can't interpret it, is really, I think, what I would say about it. And so what we've done here is I use the data synthesizer called Y-Data, and I created a bunch of other stroke-like patients, meaning it looked at the data, it created people that look statistically extremely similar to the 249 stroke patients. So now we have the same number of stroke patients as non-stroke patients. And so now let's look at the performance of that. So now you have an AUC that's higher. Classification accuracy is still high, actually a little lower than before. But notice the F1, instead of being 0.1, it's really high up there. And I point to random forest is suddenly unbelievably good. Precision 0.864 means most of your positives are true positives. Recall, you picked up most positives. Log loss is low, which it should be, because remember, it compares the predicted probabilities with the actual probabilities. So the lower the better. 0 would mean there's no difference between the predicted model and the actual model, so to speak. So a huge dramatic change since we added those synthetic patients. We're still in the process of exploring that and becoming more expert at it, so that when we get to the chapter on class imbalance, we'll have more examples and more conclusions. Let me see, we've got some stuff in. Dave, you responded, I guess. Let's see.
Yeah, I did. I answered the question so far.
On the VIP. Okay, gotcha. I have not looked at it yet. All right, but I think it's a good stopping point. We can move on, but we're almost to the hour. I really would rather spend this time talking about any questions or even concerns, because as I've said before, we are spending a lot of time on this chapter 2 for a reason. We think that if you don't understand this and you don't follow a systematic way to evaluate your data, it's going to end up garbage in, garbage out. It's, again, some of you may end up just getting ballpark stuff and then showing this to a data science. There's nothing wrong with that. In other words, where you're the first one that looks at the data and you say, I've run this classification model and random forest really gives good results. And then you go to the data scientist who picks it apart in more detail, mines deeper, and looks for some of these data traps that we reviewed today. Again, that puts you ahead of the average person. So I'm not opposed if that's all you get out of this, but What we're attempting to do here is make you think like a data scientist and maybe even use tools that they don't always use in a systematic workflow. So let me stop and ask, are there questions about what we went over today or the future direction, or any other questions about the book, the workshop, whatever? Don't be shy. And again, if anybody came in late that's here for the first time, please feel free to unmute and introduce yourself.
Bob, while we're waiting for questions, I'll make one comment. Now, when you look at these workflows, you might say, oh my gosh, this looks so complicated. What I want you to keep in mind is that when you see something like this in a book, you could easily recreate it. And we're going to also have, either on GitHub or on our book website, we're going to have these workflows that you can download. And then the only thing you have to do is plug your own data in at the far left where it says file, and everything will be done for you as it flows through this. And then you will then spend most of your time interpreting the analysis, which is the most important part, not actually doing the analysis. So we're not shortcutting the interpretation. We're making it easier for you. You don't have to write, God knows how many lines of code to create this, or how many commands and some other kind of software to create it.
Yeah, thanks. I meant to say that exactly the same thing, that if you were to do this in Python, you're talking about probably 5 or 6 hours of work at least, with probably 200 lines of code, and much greater chance of you making mistakes. So number one, we will share, once we get to the experimentation section, we will share any OWS files with you. So as David said, all you're going to have to do is plug in your data and it will do everything else for you. And you will have the ability to compare two different data sets, such as imbalanced and balanced, or you pick the comparison, but this will save you an immense amount of time. In addition, at some point, we hope to have some spreadsheets, color-coded data science experiments that you can use on your own, that'll be downloadable, probably from the file share site, where you can then start running experiments, recording what you have, and coming up with your own conclusions. I see a little bit of chat.
Yeah, there's two questions. First of all, Bob, they're wondering, where are we going to put all the OWS files? I know once in a while you send some out on email. Is there going to be one parking spot for all of them?
Well, yeah, Cass, I think what we'll do is, what my plan is to make it chapter related. If you go to the file share site on nocodedatascience.net, which is our, I'll put that in the chat. The file share has by chapter. So the plan would be to put any important OWS file and any important data set in that same chapter. That way, all you have to say is, I'm working in chapter 2. It must be in chapter 2 in the file share. I think, to my knowledge, it will accept everything. I have to today verify that I can. My only concern would be is whether it'll accept an OWS file uploaded. I'll find out. I know I can attach it to an email, but I don't for sure know that the file share site will accept it, but I'll let everybody know. I'll determine that today. Let's see, there's a question, David.
Yeah, I tried to answer it. They were asking, if the data set imbalance, what do I do? Is it worth proceeding? And my answer was, yes, it is. But what you also want to do is make sure that you look at the balancing options that we're going to talk about next month, with SMOTE and with the synthetic data, and then compare the two models. And then exactly how you compare that with our data science experiments, we'll explain in detail next month, give you examples and so on and so forth.
Yeah, but it may not be next month because we've got some more stuff to cover. We still got the orange widgets in the rest of the chapter. We're getting down to the end, but we'll see. It'll be shortly. I'll put it that way, that we'll be covering that, but that'll be chapter 6. We still have chapter 4 and 5. So more follow. Other questions and concerns? Okay, and feel free though, again, let me put in that's no code.
I think what we're going to cover next month is just kind of a top level experimental chapter, and the really deep stuff will be coming later.
Yeah, we will be covering the data science experiments for sure. That will be next month in detail. So stay tuned on that. I think you'll find that very interesting. It's meticulous, but it's really important, and it's definitely interesting and way more factual and scientific than just saying, I like logistic regression, you know. So we'll go over that. Any other questions or concerns? You have my email, and have David's too, I think.
I'll type in mine.
Okay, if there's no other discussion, then thank you for your participation. I'll have this up on the YouTube channel with an email to everybody later today. So thanks. We'll see you in a month.
Everybody, take care.
Thank you.
Have a great
Take care.
weekend.
Stay warm, stay dry.